We have studied kinematics before, but that kinematics was for constant acceleration only. Now we will start with the topic of variable acceleration. We know that if the force is constant, it produces constant acceleration. So remember, a constant force produces constant acceleration, and we have applied equations of motion before. Those equations of motion were valid only for constant acceleration. Now, if we look at this velocity time graph, we can see that a straight line is there which is passing through the origin. The gradient of this straight line is constant. That means from our basic knowledge of coordinate geometry, we know that a straight line has a constant gradient, a constant slope. We also know that the slope of a velocity time graph is acceleration. So therefore, in this particular sketch, the acceleration is constant. And we also know that if we look at a displacement time graph, the slope of a displacement time graph is velocity. That means if these sketches were there, we can use the graph to find the velocity from a displacement time graph. Similarly, we can find the acceleration from a velocity time graph. But we know that in real life, acceleration is neither constant nor it changes suddenly. Now let's understand this concept by using two examples. If we talk about driving a car, if we say that the acceleration is constant, that means the velocity will keep on increasing till it crosses the speed limit. But that's not practically how it goes. Similarly, if we talk about a lift, and if a person sits in a lift and it starts from the ground floor and we want to reach the top floor, so the acceleration does not change suddenly. If it changed suddenly, the person traveling would feel a jerk, the person would fall down, or maybe the cable in the lift could snap. So therefore, again the emphasis is, in real life, acceleration is neither constant nor it changes suddenly. Now, if we look at the graph, for example, this is a displacement time graph. That is what reality looks like. The gradient of a curve is not constant. It changes at every single point. And we know the concept of gradient of a tangent. For example, if I draw a line over here, the gradient of this line is different versus if I draw a line over here. That means the velocity keeps on changing. The velocity is variable. Similarly, if we talk about a velocity time graph, again, if I draw a tangent over here, the gradient of this tangent is different. The gradient of this tangent is different. The gradient of this tangent is different. That means the acceleration is also changing. The acceleration is a variable. So now we have to use the concept of differentiation and integration in order to solve problems related with variable acceleration. Now we know that the symbol for displacement is S, symbol for velocity is V, symbol for acceleration is A. If we talk about differentiation, if we have an expression for displacement and if we differentiate it, we get velocity. If we differentiate the velocity equation, we will get acceleration. Now, what about integration? If we integrate acceleration, we will get velocity. If we integrate velocity, we will get displacement. So now let's have a look again at a constant acceleration velocity time graph. We know that area under a velocity time graph represents displacement. Now, this velocity time graph represents a straight line. The area under a curve could be a rectangle, it could be a trapezium, and we will use the relevant formula and we'll find this area. Naturally, we can also use equations of motion based upon the information given, and we can also find the displacement. Let's revise the concept of pure maths of area under graph. For example, if I have the equation y is equals to x square, and I'm interested in finding the area under the graph between the limits 1 and 2, what we should do is to write this thing as area. The limits are 1 and 2. The function or the equation is y is equals to x square. So we will write x square over here. We will integrate it. So this will become x cube over 3 between the limits 1 and 2, which simplifies to 2 cube over 3 minus 1 cube over 3, which simplifies to 8 over 3 minus 1 over 3, which becomes 7 over 3 units square. That is the area under the graph. Now we will use this knowledge to find area under a velocity time graph. For example, if I'm interested in finding the area under the graph between these two values, let's say this is 1 and this is 2. And this is the area under the graph. So if velocity is a function of time, all we will do is to integrate this function between the limits 1 and 2, and we will find this area. So this is basically use of definite integral, that is integration with limits to find this area. So remember the rule that definite integral, that means integration with limits, it will give us the area under the graph, which is the displacement between the two values. And it can also be termed as distance as long as the particle is not turning around. What about indefinite integral? When we talk about indefinite integral, that is integration without limits, what we will do is that if we integrate a velocity equation with respect to time, we will get some terms plus a constant of integration c, and we will plug in some value of time and some value of displacement, and we will be able to find the c. So let's recap what we have studied over here. We know that if we differentiate s, we will find velocity. If we differentiate velocity, we find acceleration. In other words, v is ds by dt and a is dv by dt. And similarly, if we talk about integration, we can obtain an expression for velocity by integrating the expression for acceleration. Similarly, we can obtain an expression for displacement by integrating the velocity expression. Yes, there will be a constant of integration c. Information will be given. For example, when we talk about the velocity expression, some value of time, some value of velocity will be given to find c. And when we talk about the displacement equation expression, some value of time and some value of displacement will be given to find the constant of integration over here. That's what this video is all about.